Okay, let's go ahead and get started. I have posted some homework assignments. Oh, I should put on the board, don't forget that you have your Prepare to Learn assignment 12B. I set the due date as tonight, give you guys an extra minute to do that. I have posted some homework assignments. I told you that 17 would be probably due later this week. It involves some integrated rate law problems, some calculations. So I decided to give you a little bit of extra time on that, but there are 3 that are going to be due at the same time. So you probably want to get started on it at any rate. On the integrated rate law problems, a lot of times the way they're telling you what the order of the reaction is, because remember we have a different equation depending on the order of the reaction. A lot of times what they'll do is give you the units of the rate constant. So that's where you need to go back and see which units correspond to which. Most of the time, what I've given you is first order, and that's the one that only has units of time. So it'll be per minute or per second or second to the -1, something like that. So if you see that, it's a first order and you're going to use the first order reaction. So I'm not going to emphasize a whole lot the 0 order or the second order. You won't see 0 order from me at all, actually, because not real common. Second order and first order are more common. I'm not going to ask much in the way of second order. We will go through an example here today, though. So pay attention to the units for the rate law. The other 2 have to do with half-lives, which we will go over today. And then the last 2 sections, which cover energy mechanisms and energy diagrams and what they call collision theory, but the idea that more collisions make faster reactions and temperature increases collision. So it's connections to temperature. Chem 101 doesn't have good questions with the graphs on them. So I may post some practice problems that have the graphs that I want you to be able to interpret. I may post some of those on Canvas so that you can see the kinds of questions that you might see. I kind of want to do a quiz over this material, and I've been thinking Friday would be good because Friday I'm going to be out of town, so I could have you do the quiz while I was out of town. I may or may not do that. I'll let you know on Wednesday when it'll be, because I'd really rather have all of kinetics on there, and I don't think I can put all of kinetics on there if I do it Friday. So we'll see what happens. So Wednesday, I also give you an assignment that you will be doing while I am out of town. It may be something where you come in and somebody else will hand you something, you'll have some group work or something, or I may have a video for you to watch on that. It'll probably be a video, but we'll see how that goes. Any question? Okay. Okay, so before we go back to doing the second order one, I kind of want to review what we had done before. So let me pull this up. And so our first question is just to look at a graph or a description of a graph. The plot of concentration versus time is linear. So when we say linear, we mean it's a straight line. What does that tell us about the reaction order? We show of fingers, what is the reaction order? Not sure, check with your notes. I see a few fingers. Check with people next to you. What do they think? Seeing a lot of good answers, a lot of one off of them. Okay, so remember, this is the plot that we would have just of our basic data. And normally our basic data is what? Linear or curved? Normally it's curved, right? That's what we looked at, where we can see like the average over the time and initial or whatever. Normally it's curved. So this is not the normal situation. So does that make any of you rethink your answers? Okay, so I'm seeing a lot of this. It's a 0 order reaction. Okay, so what this is telling us is that the slope is constant, and the slope tells us the rate. So the rate is constant, and if the rate is constant, that is, it doesn't change, no matter what the concentration does, then it's a zero order reaction. So if we were trying to calculate how much was left over after a certain amount of time, we'd have to use one of these equations. Which equation would it be? How many of you think it's going to be equation A? How many think B? C? All right, so the majority is right. Yeah, this is a description of this graph. So this is the y-axis, A at time t, and this is the slope, negative k, and t is the x-axis. Okay. All right, so next question, I'm telling you it's second order. The graph for a second order reaction looks different from the other two. Like just right away, there's a real obvious difference. What's the difference? The slope is positive. Okay, so positive slope, what does that mean? How is it visually going to look different? Yeah, the slope is going up instead of down. So I guess in your direction, it's going this way. All right, so our graph looks like this instead of being downhill like all the others. And that's because we're doing 1 over here. All right, and I think I kind of gave away the next question. So which is the integrated rate law that we use for second order reactions? C, yeah, it's the one that has 1 over AT. Okay. And then finally, if the graph of a concentration versus time is curved, so in lab this week, you're going to be collecting some data. If it's linear, you know it's zero order, but if it's not, then you're going to test the concentration versus time, the natural log of the concentration versus time. If that turns out to be linear or a straight line, what does that tell you? What order would it be? So we've already done 0 and we've already done 2. So what's left over? 1. This would be first order. Okay, so which of these laws would be appropriate? Or equations, I guess. B. Yeah, the obvious. Okay, little note about, is that my last question? No, I did have one. Okay, little note about when you are doing your test of is it a straight line. Sometimes you're going to have data points that are kind of all over the place, and you're going to do what's called a best fit line. So it'll go kind of through your data points. Now, if, and it should, I did that a little bit off, so probably the curve is a little bit like that. Okay. If when you are looking at this line, you have data points all the way along that are both on top and bottom, then that's probably a good indication that it's a straight line. But what you sometimes see is that if you have a curved line that's pretty close to linear, you might think, oh, that's going to be a straight line, but you can look for something that will tell you that it's actually not. So if you have something like this, so that's pretty close to linear. My straight line has the points above the line are on the tails, and the points below the line are in the middle. And this indicates to me that this is actually curved. So when you're in lab and you're checking to see is this linear, take a look at where the data points are falling with respect to your best fit line. So if they're kind of scattered, it's probably linear. But if you have some that are above only at the ends and the ones that are below the line only in the middle, then it's probably curved. Okay, now let's try a practice calculation. So we did first order reactions on Friday. Let's try one more first order. And I've picked the equation for you, so you don't have to pick it out. Initial concentration of technetium-99 is 0.44 molar. The rate constant for the first order decay is 0.0019 per minute. What is the concentration after 120 minutes? Okay, so you have this law here. And then you want to plug in things. I meant for this to pop up after you had a chance to plug those in. But it says the initial concentration, so I plugged that in for A0. K is the rate constant, so I plugged that in here. And I was running out of room, so I didn't put per minutes. But if I had per minutes here and minutes here, those two would cancel out. And then I had 120 minutes. All right. So what do you get for natural log of the concentration at time t? Best way to learn these things is to go ahead and plug them in, try them out, have it become muscle memory. Like you learn to ride a bike better by riding a bike. You'll learn to do this better by doing this. All right, anybody have a number for me? Still working. Okay, I'll give you another minute. All right, so just the natural log, just solving for the left side of the equation. Did you get a negative number? You should have gotten a negative number. All right, so Danielle, what did you get? Negative 1.0. Negative 1.0. Anybody else get negative 1.0? Okay. So I got 1.05. I left an extra digit on there. You would round it to the even, which would be the 0. So that is the appropriate way to round it. Now I left that extra digit on there because I like to round at the end. All right, how do we know this can't be the concentration? Because it's a negative. We can't have a negative concentration. The other thing we can look at is, even if we didn't notice that it was negative, our concentration is supposed to go down. We started at 0.44 and this is 1. So that doesn't make sense unless we remember that it's negative, in which case that doesn't make sense. All right. So anybody have a final concentration? Oh, well, what do we need to do in order to get the final concentration? We need E. So you should have a button on your calculator that is a lowercase e with an X, and it's usually the same button as the natural log. You just have to hit shift. So you're going to, depending on whether you have a small calculator or a graphing calculator, you would put them in a different order. But you're going to do e to the negative 1.0 or negative 1.05 or negative, or e to the answer, which is what I did. So I got 0.35 because I just had the calculator use what the answer was before. If you had plugged in e to the negative 1.0, you might have gotten something slightly different. And this makes sense because it's positive and because it's a little bit less than the original concentration. Okay. So whenever you see anything about nuclear decay, so this is an isotope symbol. Remember, isotope symbols have the mass up in the upper left-hand corner. We looked at those way at the beginning of the year. When we see an isotope symbol, that means it's nuclear decay we're looking at, and they are all first-order reactions. Okay, and that's going to make sense when we start talking about half-lives, because you've probably heard of half-lives in reference to nuclear decay before. All right. Now let's get back to that question that we had that was a second order question on your sheet. That one. Okay, we were at this one. Not too far. Okay. The rate constant is wrong on here. Let me see. It should be 1.6 times 10 to the negative 3. And on your paper, it says something different. So on the last question, change, oops. Stop going all over the place. Change your rate constant to 1.6 times 10 to the negative 3. Okay, so HI, hydrogen iodide, breaks down into H2 and I2 at a rate of K is equal to the concentration of HI squared. So that tells us what's the order? 2. It's since it's squared, it's second order. And then the rate constant is, as I said, 1.6 times 10 to the minus 3. And so we have our question, if we have 0.0100 moles of HI and we place it in a 1 liter container, so then the concentration then is 0.0100 moles per liter, right? Because it was in 1 liter container. How long will it take for the concentration of HI to reach 0.00900? Okay, so to go down by about 10%. Now, since this is second order, we're going to use the equation that involves 1 over A instead of natural logarithm. So that's what makes this one different, is that we're doing the second order equation. Now, when we plug these in, remember that to take the reciprocal of a very small number, we're going to get a really big number. So we're going to have big numbers that we're dealing with, but we're going to be subtracting them from one another. So it'll end up working out. Okay. So this lists all of our data. K is equal to 1.6 times 10 to the minus 3. The original HI, or the initial HI, is 0.0100. And then we're actually given HI at time t. Okay, so we're looking for t instead of looking for the concentration. So we have this number, and the K, and we're looking for the T. So probably the first thing we want to do is find the reciprocals of those concentrations and subtract them from one another. And that way we can get KT by itself. All right, so take a moment to plug these things in, see what you get. Okay, so for my reciprocals, I get 111 and 100. Is that what you got for your reciprocals? Okay, so I subtract those and I'm basically getting 11. Okay, so 11 is equal to 1.6 times 10 to the minus 3, and I left off a t there. Obviously, that's not a true statement if I don't put the t in, so let's do that. And then I end up with 6,875 seconds. So this is actually a really slow reaction. Now, if we have that many seconds, we might be saying, well, wouldn't there be another unit of time that might be a little bit more convenient to look at? So we could look at this in minutes. How could we change seconds to minutes? Divide by 60. So that's about 114 minutes, a little less than 2 hours. All right, so for integrated rate laws, the first thing is to know which order of reaction that you're looking at. And you will on quizzes and tests just have some questions like we did at the beginning. Look at the graph and tell me, or look at the equation and pick the, or look at the problem and pick the right equation, that kind of thing. And then to just plug things in and make sure that you undo the last several things. So for example, if you're solving one of these for the concentration, make sure you take the reciprocal at the end. If you're doing a first order, make sure you do e to the at the end, so you don't end up with a negative number. All right, anybody still need this slide? All right. Let's switch gears. Oh, wait, I didn't need to switch. I just needed to go to the next slide. Okay, so half-lives. Half-lives only really matter for first order reactions. And that's because for 0 and second order reactions, they're not constant. They change every time we change our concentrations. But we're going to find something for first order reactions is that they don't change the amount of time that passes depending on the concentration. So let's look at what I mean by that. So we have an initial concentration here of 0.06, and you can tell this is about halfway, right? Halfway down from that is 0.03. And if I look at how much time passed and come down to here, this is 24. It happened to be 24 minutes. 24 minutes to go from halfway, or to go from full to halfway. Now, what's half of 0.03? 0.015. Okay, so about this much. And the 0.015 is in between these two parts here. If I go over here and go down, this says 48 minutes. So 24 is half of 48 minutes, right? Okay, so I've just taken twice the amount of time to go to a fourth that it took to go to an eighth. Or if I look at it this way, if this had been my starting amount, it would have taken me 24 minutes. So it took the same amount of time to go halfway, whether I was starting at 0.06 or 0.03. So let's see if this holds true for the last little bit. So this is 0.015. Half of that is going to be 0.0075. So it's going to be less than 10, but not halfway between 10, but 0.01. Less than half, it's going to be less than 0.01, but about 3/4 of the way up. So we're going to go all the way over here, and this is 72. Okay, so 72, that's another 24 minutes. Okay, so for first order reactions, that's going to be pretty constant. Now, by definition, regardless of the order that we're dealing with, the half-life is the amount of time for the concentration to decrease by half of the reactant. And it's represented by the symbol T with a little 1/2 next to it. It's a very common mistake for people to think that this means half of the time. It is not half of the time. This is just a symbol. The whole thing, including the half, is a symbol that refers to the half-life. So when we see this in an equation, we're not going to do anything with that half. We're just going to carry it around as if it was a G or an F or something like that, like the temperature of the freezing point. We had a little F there. It's a label. All right. And so if this is a first order reaction, the same amount of time would be required to go from 1/2 to 1/4. All right, we good on this one? Okay, so this is just carrying that same definition so that we don't forget what we mean by it. Now, we're going to take a hypothetical. Suppose I start with a concentration of 100 mole. Now, that's kind of a big concentration, but it's going to make our math easy here. Okay. And I'm going to use the first order rate law that looks like this. So remember, we had two. One of them had that kind of subtraction thing going on. The other one had the A0 and AT on the same side in parentheses. So we're going to put them together over here. All right, so somebody's noticed something interesting here. I have AT on the bottom and AO on the top. What else is different on the other side? I dropped the negative, okay? So if you don't get logs, just trust me, it works out. If you do get logs, it's because I changed the order that I was subtracting. All right, so I'm going to plug in my numbers. My initial concentration was 100. And then, of course, halfway, it's going to be 50. So what I really have is that my half-life is the natural log of 2 divided by k. Now remember that 1/2 isn't anything we need to do mathematically. It's just a label that's saying this is the half-life, okay? But I've got a natural log of 2 and I'm dividing it by k. Now, if I had started with 75 molar and put in half of that amount, or if I'd started with 4 molar and put 2 on the bottom, or if I'd started with 0.1 molar and put 0.05 on the bottom, would that have changed the natural log 2? No, it just always is going to end up being natural log of 2. So this is a constant. So that means that when I have a first order reaction, I don't need to know anything else about it. All I need to know is what K is, and I can figure out the half-life. And that's exactly how nuclear reactions work. When you talk about the half-life of a nuclear decay, they decay according to first order kinetics. And so the amount of time it takes to get halfway down is always the same. So if you've heard of radiocarbon dating, this is where they figure out how old something is that has carbon. And the way that we can do that is that carbon in the environment is constantly being exchanged with the air. So you're breathing out carbon dioxide, you're eating food, plants are producing that food, they're producing carbon dioxide. They actually do respiration too. So they produce carbon dioxide, but they also take it in from the environment. So we're constantly exchanging it. In the atmosphere, the carbon that that is in the atmosphere. Some of it comes from the nitrogen gas. So nitrogen makes up most of the atmosphere, about 80%. When ultraviolet light hits it, occasionally it will turn into a carbon-14. Now, when I say carbon-14, what does that mean? It is an isotope. The normal isotope, the 99.9% of the time isotope is what? Carbon-12. So carbon-14 is pretty unusual, but it's constantly being made in the atmosphere. So it's constantly being replenished. But if I take a tree, say, and I chop it down, now that tree isn't exchanging carbon with the environment, and I turn it into a table, okay? The carbon-14 in that wood is going to be decaying, and it's not going to be replenished. And so over hundreds and hundreds of years, that wood will have less carbon-14 in it than a table that was freshly made, okay, out of a freshly chopped down tree. And so they can use the difference between those to figure out how old the wooden handle on a gun is, a chair is, cloth, if they have enough organic matter from some living thing. So the half-life for carbon-14 is not quite 6,000 years. So we can date things pretty far back. But the window on how close we can get is really just about 20 years. And that's assuming we have enough material that we can really get a lot of significant figures. So if I only have a teeny tiny amount of material, I might only be able to tell within a couple hundred years. So I'm not going to be able to tell the difference between a tree that was chopped down last week and one that was chopped down the week before. That's too close in the amount of time. And that's where half-lives are important, is that it helps us to understand what is going to be the window in which we can understand things. Okay, point of all this is that the half-life does not depend on A in brackets. And what do I mean by A in brackets? Concentration, exactly. Okay. So let's do an example of the equation that we just saw. I have a certain reaction. It's determined to have a rate constant. What's the letter that I use for rate constant? K. So K is 0.0116 per minute. Now notice the units here only have time, per minutes. That's the indicator that this is first order. And I want to know what the half-life is. All right, so I need my equation. So this is one way to write the equation. On the previous page, I had it rearranged so the K was on the bottom, which you can do. And we're just going to plug in ln of 2, and we're going to plug in K. Now, on your calculator, when you do a natural log, it's going to open the parentheses. You need to close it. If you don't close it, it's going to think K goes in that parentheses. Okay, so we're going to plug in ln of 2, close the parentheses, and then divide it by 0.0116. And I think, actually, let me just plug it in. Okay. Sometimes you will see this equation written as, instead of natural log of 2, they write 0.693 divided by K. The natural log of 2 is 0.693. That's where that number comes from. For me, it's easier to remember the equation with the natural log of 2 because 2 is part of 1/2. So, all right, so I plug that in. I get a half-life of 59.7 minutes. Is that what you got? Excellent. All right. So we know that we can get our half-life that way. Sometimes we'll have, like with nuclear reactions, we know the half-life, but they don't tell us the rate constant. So if I wanted to use the rate constant to solve an integrated rate law problem, I could reverse this and find K instead. So let's say I have a reaction that has a half-life of 13 minutes. The reactant has an initial concentration of 0.745 molar. That's A at time 0. And I want to know the concentration after 26 minutes. Now, there are a couple of ways that we can solve this problem. I'll let you get the information down before we go through how to solve it. So the traditional way we would do this, like I said, we need to have K to know what to plug into our rate law equation. If they're telling us there's a half-life, then it's probably a first order reaction. So I'm going to use my first order reaction where A at time 0 is 0.745. The amount of time is 26 minutes, but I need to solve for K. So first I'm going to plug into my equation with the half-life to figure out what K is. Okay, so I start with this same equation, but now I'm going to divide by T half. And remember, I'm not going to do anything with the half. The half is just a label. All I'm going to do is divide by 13. And plug that in and see if you get 0.0533. And I'm carrying an extra sig fig there than I should, but should get right about that. And if you're not getting that, make sure that you close the parentheses on the 2 so that you don't have the 13 in the parentheses. All right, anybody get that for K? Got a few nods out there, excellent. All right, so now that we have K, then we can plug it into our first order equation. Remember, our first order equations are the ones that have the natural log in them. So I'm going to have natural log of A at time T. That's what I'm looking for, is equal to natural log of my initial concentration minus the rate constant 0.0533 times the time. All right, is that a reasonable concentration? No, because it's negative. So we look back at the beginning, oh yeah, we haven't actually found the concentration yet. We're still in natural log mode. So what are we going to do to undo it? E. We're going to look for E on our calculator, lowercase e, not capital E, and do E to the negative 1.7. And I get 0.18. Anybody else get 0.18? Good. Okay, so this kind of question looks like one question, but really it's two questions. The first part of the question was find K, and the second part of the question was, okay, now that I have K, let me find the answer to what they were asking. All right, so the other way to solve this is if we notice the relationship between the half-life and how much time has passed, right? Because if they had said, what's the concentration after 13 minutes? We could say, well, after 13 minutes, there should be half left. I just have to take half of the original. So what is 26 related to 13? It's twice that, right? So we have 2 half-lives have passed. So if 2 half-lives have passed, then I take my original concentration, cut it in half, and then I cut it in half again. Oh, I thought I had that written on here. So if you take in your calculator 0.745 and divide it by 2 and then divide it by 2 again, you should get about 0.18. Or if you just divide it by 4, you should get about 0.18 because 1/4 is half of a half. So sometimes that's a way to speed up a problem, particularly if you have like a multiple choice test on a standardized exam. They might be looking for you to recognize that rather than taking the long way around. So that can be a way to speed things. All right, you don't need to write any of this down because this is just showing you that it doesn't work for 0 order or second order, okay? So if we kind of follow the same logic for 0 order, if I do the half-life starting with 2, I get 1/k, but if I do the half-life starting with 100 molar, I get 50/k. So I don't have a constant thing. It depends on what my starting number is. Half-life depends on concentration. Second order, same kind of thing. I can plug things in. I plug in 100. And my half-life, this one is just solved for whatever the original concentration is. Depends again on that original concentration. So we don't talk about half-lives with second order. It's kind of like Bruno. All right, so let's do one more example here. The number there is the problem from the old book. I should erase it from the slide. A first order decomposition reaction. So we know we're dealing with something that half-lives are appropriate. We know we're dealing with the natural log equations. The first order decomposition reaction has a rate constant of 0.0012 inverse years. And we have 2 different questions to answer. So one is, what's the half-life of the reaction? And the second, we're looking for the amount of time that it takes for the reactant concentration to reach 12.5% or 1/8 of the original amount. Oops. I thought I had that in there. Okay. I'm gonna have to do this one on the board. All right, does everybody have the data they need from up here? So the first question was find T1/2. Remember, this half is just a label. We're not going to do anything with it. It just tells us the half-life. And we know that we have natural log of 2 is equal to KT. So we're going to have to take natural log of 2 and divide it by K. And I get 580 years. Anybody else get that? Okay, excellent. We're all on the same page. Okay, so that's the answer to the first part. The second part asks us, how long does it take us to get down to this 12.5%? So there's a couple ways I could answer this. One way is to notice that they tell us 3 half-lives. Okay, so 3 half-lives just means 3 times 580 years. $1,700 years, and the reason I dropped the 40 is to keep with just 2 safe things. The other thing I could do would be to plug into the equation that I have concentration, so I want a natural log of, let me use this form, natural log of A T over A 0 is equal to negative KT. So I have natural log of 0.125 A0 over A0. Those cancel, equals negative KT. Natural log of 0.125 divided by negative 0.0012, and that's going to give me my time. I get 1732, which rounds to 1700. Right, so you can do it either way. But if the fact that they gave you a percent scares you, you can always go to the law. The last 2 sections we're covering on Wednesday. And I will see you then. And start looking at the integrated rate law problems now, because you don't want to get that mixed up with Wednesday.